Hey guys, this is Coach Lowe, and we're going to talk a little geometry again today. So we're in Chapter 2, Section 1, and we are going to talk about inductive reasoning and conjecture. So Chapter 2 is going to be a little bit different than what we did in Chapter 1. It's a little bit of reasoning and proof, so some kind of fun times ahead for you guys. This is great. All right, so first of all, let's talk definition. What is inductive reasoning? So remember, you need to have a composition notebook. You can also put this on a slide if you want to. You can take notes on paper and put it in Google Slides, but my preference is you have a composition notebook or you're using the notebook on Google Slides. That would be awesome. All right, so definition, inductive reasoning uses specific examples to arrive at a conclusion. Uses specific examples. Oh, good. Nice spelling. Let's try that again. Uses specific examples to arrive at a conclusion. All right. So let's talk about as we do these specific examples and we figure out the pattern, because that's basically what we're going to be looking at. What is it called when we get to the end and we go, okay, this is the pattern? Well, sometimes we call that the conclusion or the concluding statement. So also the concluding statement, you'll see on the instructions, they'll call it a conjecture. So they'll say, write a conjecture for, and what that means is look at the pattern and then figure out what the pattern is and then tell what the pattern is. And then they may ask you to find, a couple of numbers in the pattern or whatever. So let's do an example of that. So here's example number 1. And I'm going to give you some numbers. -4. See if I can get that black off of there real quick. There it goes. -4. -1, 2, 5, and 8. All right, so what is the pattern? If you want to pause the video, you can. What is the pattern? And then can we find the next term? So the instructions, instead of saying what is the pattern, it'll say write the conjecture for this number, for these numbers, and then maybe find the next 2 terms. So what is the pattern? Well, we see that we go from -4 to -1 to 2 to 5 to 8. So do you see that we're adding 3? So my conjecture is add 3. Right? And then can we find the next term? So if I'm going to add 3, what would be this next term? Let's just go ahead and do the next 2. So the next term would be 11. So 8 plus 3 is 11. And then the next term, 11 plus 3 is 14. So that would be the conjecture, adding 3 to each term, and then the 2 missing terms. So the next 2 terms would be add 3 to 8 and then add 3 to 11, and that gives us the next 2. All right, what about this one? This one's a little bit different. I'm going to go ahead and change to green because I know that blue is a little bit hard to see, even though I love it. Angle DEF is a right angle. Angle DEF is a right angle. All right, so what kind of conjecture could we make out of that information? So there's a geometric relationship here. Well, what is it? I say we draw a picture. So angle DEF is a right angle. So we know that it's going to make an L shape here. So go ahead and draw your picture. And what's that symbol that we put on right angles? Yeah, exactly. That little box in the corner. And I'm going to go ahead and label this DEF. All right, so looking at this picture now, what conjecture could we make? What do we know about the rays that form this angle? What could you tell me about ray ED and about ray EF? Well, I know that ED is perpendicular to EF. Because if I have a right angle, I also know that perpendicular segments, lines, rays form right angles. So I know that ED and EF must be perpendicular to each other. Remember, that's the symbol for perpendicular. All right, so let's move on to another vocabulary word, and then we'll be finished. So counter example. If you are asked to find a counter example, what do you think that means? I know you've probably heard that before. A counterexample means it's a false statement or false example to show that a conjecture is not true. So like our pattern that we found, we would find a counterexample. If we wanted to prove that wrong, we could find a counterexample, and that would show that my statement is not true. So a false example to show that a conjecture is not true. All right, so let's look at an example real quick. This first one, if angle RTS and angle STU form a linear pair, then angle RTS has to be congruent to angle STU. Then angle RTS is congruent to angle STU. What do you guys think about that? Well, first of all, we probably need to talk about what linear pair means, don't we? So what is a linear pair? So if you need to look it up, then please look it up. A linear pair means we have two angles that share the same vertex, are adjacent to each other, and the backside of those angles forms a straight line, the rays. So this would be RTS and then STU. Go ahead and put these on here. And so you can see these guys form a linear pair, right? All right, now I specifically drew this example so that these are not congruent to each other. So the question is, this is my counterexample. The question is, RTS and STU, do they form a linear pair? The answer is yes. When I add those two together, they add to be 180. TS is the shared ray. They share a vertex, and the rays that they don't share, or the ray that they don't share, TR and TU form a straight line, right? They're a straight angle on the back side. So angle RTS and angle STU are not congruent to each other. So this would be my counterexample. Now, could we draw one that would work for this? Absolutely, right? They would both be 90 degrees. Absolutely. We could draw one example that would work. That's not what I asked for. My question is this true all the time? And the answer is no. To prove that something is not true all the time, you just need one counterexample. So I only need to draw one. Yours may look a little bit different than mine, and that is totally fine. All right, here's the second one. If RT plus TP equals RP, then RT is congruent to TP. All right, again, draw a picture. You're going to hear me say this a lot this year. Draw a picture and let's look at this. All right, so let's get a number line going, or not a number line, let's get a segment going here. So I have RT, and then I'm going to go ahead with T to P, right? And it says if RT plus if RT plus TP equals RP, which means I have these sections, right? RT plus TP equals the whole thing. All right, so there's our little segment addition property. Then RT is congruent to TP. When would that be true? When T is what? Yeah, when T is the midpoint, this is true. Is T always going to be the midpoint? No, the picture that I drew, T's not the midpoint. So if this whole thing is 15 and this part right here is 6 and this is 9, that adds to be 15. Those two are not congruent to each other. So there's a counterexample of RT plus TP equals RP. That first part is true, the hypothesis, which we will talk about soon. I set this up so the first part is true, but I found a counterexample where the last part is not true. The last part is false. Same thing on this first one. I found an example where the first part was true. So I drew an example where this part was true and this last part was false. All right. Hope that makes sense for you guys. If you have any questions, make sure you write it in the margin of your notes. And your assignment is posted with this video on Google Classroom. So look at the top of the post and you'll be able to find it. This is Coach Lowe and I'm out.